We're now ready to look at the harmonic oscillator through a quantum theory lens. So I'll remind you that the energy expression that we have for the harmonic oscillator looks something like this, where we've got 1 over 2 mu times the momentum of the oscillator plus 1/2 mu omega squared times the coordinate, and I'm going to use x now as the coordinate, the displacement coordinate for the oscillator. So when we convert a classical energy expression to quantum mechanics, okay, this involves writing down the Hamiltonian operator, and we can use this direct correspondence to write our momentum operator as minus h bar squared d squared dx squared. And our position operator is simply the position coordinate. So this would be our Hamiltonian for a simple harmonic oscillator, and the one that we would use in the Schrödinger equation. So in our Schrödinger equation, we might write something like this. H times psi equals minus h bar squared over 2 mu times the second derivative of our wave function plus 1/2 mu omega squared times x squared times our wave function is equal to E times our wave function. Okay, so this is an eigenvalue equation where these E's, the energies, would be the eigenvalues. Now, it's useful to rearrange this, and so I will, to isolate the second derivative term in one place, and basically I'm multiplying through by minus 2 mu over h bar squared. So when I bring this term over to the other side, I'll end up with a plus 2 mu over h bar squared times a quantity that looks like energy minus 1/2 mu omega squared x squared, multiplying the function psi of x. All right, so this is a second order differential equation for psi. Now, this looks a lot like the classical wave equation and it has many similar features, but one thing it has that the classical wave equation does not have is this term here. It does not have a term that depends upon the coordinate in this part of the differential equation. And this is the part that makes the harmonic oscillator a little bit different. It also makes it a little bit more difficult to solve. However, having said that, I want to express that the harmonic oscillator Schrödinger equation is one of the handful of problems that actually can be solved exactly. We're not going to do that in this class, but I want you to know the solutions exist. They're not necessarily that difficult to derive, but it is a little tedious to go through the algebra. So what I'm going to do is simply quote the results for the harmonic oscillator, and I'll just say that you can find plenty of sources online or in textbooks that will show you how to get those solutions. All right, most importantly, the solution for these eigenvalues, these energies that satisfy the harmonic oscillator Schrödinger equation, have a very simple formula. They're equal to h bar times the harmonic frequency times n plus 1/2, where these values of n can be 0, 1, 2, and so forth, all integers. All right, so this is maybe the central result that we need to know for harmonic oscillators, is that their energies look like this. I've drawn a picture over here on the right-hand side which shows the first 4 energy levels relative to one another. And so we can see sort of how they shape up in the potential surface, which I've drawn here. So this is basically V of x shown here for the harmonic oscillator with its various energy levels drawn inside. And there's a couple of points that I want to make in particular about this. One of these involves the difference between adjacent energy levels. So if I took the energy level corresponding to the number n plus 1 and subtracted the next lower energy level, what would I get? Well, I'd have h bar omega times n plus 1 plus 1/2 minus h bar omega times n plus 1/2. Well, I think it's pretty easy to see that the h bar omega times n plus 1/2 in both of these terms vanishes, and the one thing that's left is h bar omega. And you'll notice that this does not depend upon the number n at all. Okay, it is a constant, which tells us that for any 2 consecutive energy levels in the harmonic oscillator, or successive energy levels, their spacing between them is going to be constant. Now, I want to emphasize that this is not common among quantum mechanical systems. The harmonic oscillator is one of the very few systems that features energy levels that are displaced relative to one another by a constant. And you can see that here. This gap is the same as this gap, which is the same as this gap, which is the same as this gap. All of those gaps are the same. Now, another thing that I'd like to point out here is that the lowest energy level, so we'll call it E sub 0, is not equal to 0. This is also true of the particle in a box, but you'll find that there are some quantum mechanical systems for which the 0 in energy, the lowest energy level, is at the bottom of the potential. This is not true for a harmonic oscillator. There is a little bit of gap. This is something called the 0-point energy. And it also means that when we talk about the dissociation of an oscillator, this is also going to be true of other oscillators, that the energy to dissociate the molecule actually starts at this energy that's above the minimum of the potential well. So it's not exactly equal to what you would find as the classical dissociation energy, for that potential. Now, finally, I want to mention that because omega can be written as 2 pi nu, that we can also write this energy, this set of energy levels, in a little bit different way. If I wrote it as in terms of in terms of 2 pi nu, I could write h bar omega n plus a half, but that's going to be equal to h bar times 2 pi nu times n plus a half. But remember, h bar is just h divided by 2 pi. That's what h bar is. So when I multiply by 2 pi, this just becomes h nu times n plus a half. Now, another way that we're going to be writing this sometimes is to use something called a wave number. All right. Now, you may recall that lambda times nu is equal to the speed of light, and so we can often also write something as when I want 1 over lambda, that's equal to nu over c. So if I want to express somehow my energies in terms of 1 over lambda, I'm going to want to use this kind of expression, and 1 over lambda is something that we refer to as nu with a tilde over it, all right, which is basically a wave number. It's typically reported in units of inverse centimeters, so you may be familiar with this from infrared spectroscopy. But this is what it's equal to. It's equal to nu over c. So in other words, nu is equal to c times the wave number. So that means I can take these energy levels for the harmonic oscillator and also write them in terms of hc nu tilde n plus a half. So there's 3 different ways that we've shown here to write the energy levels of the harmonic oscillator, but they really only vary in the units that you would express them in. So we would typically use this one if we wanted to express the energy in units of inverse centimeters. We might use this one if we wanted to express the energy in terms of, for example, inverse seconds.